Okay, Tyler, so I think this is where we picked up. I apologize if it's a little cloudy. I actually had to take pictures of these on my other tablet, and it's a long story. Anyway, so I'm going to pick up right here with this Leibniz's theorem, which basically says that if you have, you can read it, if you have an alternating series, that means the signs alternate, and if you see the terms decreasing, then it's going to have to converge. So just as an example, here's kind of a series that we can make from this repeating decimal. Let's suppose we had this 0.23 repeating. So we can start off by writing it as 23 over 100. That would take care of just those first two terms. Plus 23 over 10,000. Now I would pick up the next two terms. And then, of course, if I add a couple more zeros onto that, now up to 23 1/millionth. But the reality is, our initial term here was 23 over 100, and it looks like we were basically multiplying by 1 over 100, so that was our common ratio. So basically, this leads us to a geometric series. And if we did 23 over 100 as A over 1 minus the common ratio, we would get 0.23 repeating. And so that kind of shows you that as those terms continue to decrease, 23 over 100, 23 over 10,000, 23 over a million, since they decrease, we know that we have a geometric series, and we know that it's going to converge. The question just is, what does it converge to? And so anytime we're looking for the convergence of a geometric series, A over 1 minus R is where we want to be. Okay, so let's look at some other stuff here. Basically, the next thing we did in class was we looked at what we already knew, which was we know that 1 over 1 minus x is represented by that series right there, 1 plus x squared, so on and so forth. And so what we have here technically is that we have an initial term of 1, and then the common ratio is basically x, right? Because if you think about it, your first term is 1, you multiply that by x, you get that. You multiply that by x, you get x squared. Multiply that by x, and you can kind of see the terms of this series. When we add them up, obviously that just creates the sum, right? So what we can do is we can go from A over 1 minus R to 1 over 1 minus x, simply because R is the common ratio and R is x, right? So that's kind of what we want to know from now on. We want to know that this and this are basically the same thing. That's kind of a big deal. Now remember, I'm stopping it here as I'm showing you after x cubed. Imagine if we kept going, x to the 4th, x to the 5th, x to the 6th, so on and so forth. So this graph down here shows you how accurate this could be. The blue graph is 1 over 1 minus x. All those dotted lines there are basically just this series with one additional term added on each time. So you can see how bad of an approximation it is right here when we only stop at x cubed. But then as we make our way up to this guy right here, now we're up to x to the 5th. So that's just stopping at x to the 5th. Imagine if it was ending at like x to the 19th. It's just going to keep drawing itself closer and closer to this curve. Why is that important? That's because we say that this series is good for an interval of convergence of -1 to 1, which means it's only a good approximation in here. Outside of that interval, it's not. And you can see, because look, here's the other branch of that curve. So that part of the curve, 1 over 1 minus x, isn't approximated very well by these polynomials. So that was kind of just a quick little, that was how we kind of started the class on Wednesday. And then what we really spent more time doing is manipulating a series and turning this series into other series. So let's take a look at that. So we said, how could I get a series for 1 over 1 plus x? And I said, well, the long way is you could do long division. I don't think you'd want to do that. But basically, you'd say, what do I have to multiply 1 by to get 1? And so you'd say, well, I guess you'd have to multiply by 1. Then you come in here and you go 1 times 1 is 1, 1 times x is x. And then we'd have to subtract. So the 1's cancel, and now I'm left with negative x. Now it's, okay, what do I multiply 1 by to get negative x? And that answer, obviously, is negative x. So we keep coming back here. Now we're here. X's cancel out. 0 minus negative x squared is positive x squared. And you can kind of see how this is going to take off. So I would never ever want you to do that. So instead, what I would rather you do is that you actually manipulate what we already know. So this series is 1 plus x plus x squared plus x cubed forever and ever, right? So what would happen? How do I turn this into 1 over 1 plus x? Well, the answer is you go back into your thinking, a over 1 minus r, right? What they're doing, it looks like, to turn 1 over 1 minus x into 1 over 1 plus x, looks like they're just doing this, right? Which means all we're going to do is go into this series right here and replace that one, all the x's, with a negative x. So it would be this. So we'd have 1, right? But then instead of an x, we'd have a negative x. Instead of an x here, we'd have negative x, right? And we could keep going. So let's just stop again after 4 terms. So what does this turn out to be? Well, the 1 stays, but then you have minus x. The negative x quantity squared turns into plus x squared. Negative x quantity cubed is minus x cubed. So voila, what you just did was you created a power series for an entirely different function, 1 over 1 plus x, all by just making a subtle adjustment to the 1 minus x on the bottom. And we carried that over. Whatever we do to the left, we do to the right. And that's kind of how we started that off. So that was one example. Let's look at another one. Let's suppose we wanted to get a power series for 1 over 1 plus x squared, right? Well, for that now, we would have to go from 1 over 1 minus x to 1 over 1 plus x, and then go one step further and say, now I got to make it 1 plus x squared. So let's think about what we know, right? Let's kind of change the color up here, right? We know that this guy is 1 minus x plus x squared minus x cubed, dot, 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 right? So imagine what would happen if now we replaced all the x's with an x squared in that series, right? So 1 minus quantity x squared plus quantity x squared minus quantity x squared cubed. So what would our final series be here? It would be 1 minus x squared plus x to the 4th minus x to the 6th, so on and so forth. So you can kind of see this is just an example of what we call manipulating a series. And what we're really doing is we're just kind of continuously changing r. That's really it. Okay, one more. Now this is something that's going to take some getting used to. It's not the easiest thing in the world, but basically for this 1 over 1 minus x to turn into 1 over 1 minus x squared, what you'll find out is that that's the derivative of 1 over 1 minus x. Real quick, here you go. 1 minus x to the negative 1, that's f. F prime be negative 1, 1 minus x to the negative 2nd times negative 1. And so what is that? That's positive 1 over 1 minus x squared, and that's exactly what we see here. So if you think about it, right, all we would need to do to go from 1 over 1 minus x to 1 over 1 minus x squared is differentiate. So we know that 1 over 1 minus x is this, right? So that means the derivative then, let's change the color up again, would be, this goes to 0, so that's not there, right? The derivative of x is 1, the derivative of x squared is 2x, plus 3x squared, and so on and so forth. So there would be your series that corresponds to that function. So there's a lot of side-by-side going on here, where we're taking one function and trying to create another function. There's a lot of different methods. First examples, we saw algebra. Here we're seeing a little calculus by differentiating. So what do you think can happen? If we can differentiate both sides, right, then we can also integrate. So let's take a look at that example. So how do we get from 1 over 1 plus x to ln of 1 plus x? You integrate, right? So 1 over 1 plus x was equal to, remember, 1 minus x plus x squared minus x cubed, so on and so forth, right? So now, all we would have to do is, if we integrate that, we get ln 1 plus x. So that means if whatever you do to the left, you do to the right, x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, dot, dot, dot. So this series right there can be used to approximate ln of 1 plus x. And so the convergence, in other words, when is this series good, is always good for the same interval that the original one was. So right now, all you guys know is from negative 1 to 1, so that means ln of 1 plus x can be approximated using this series right here, negative 1 to 1, and it'll give you a pretty good result. So let's finish up here. This guy was an arctangent example, right? The integral of this is arctangent. So a minute ago we found that series, 1 over 1 plus x squared. This guy, if you remember, was 1 minus x squared plus x to the 4th minus x to the 6th, which means if I integrate that, right, let's kind of change it up here a little bit. If I integrate that, right, that means I'm integrating that. So the series that corresponds to arctangent would be x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. And again, you know, convergence takes on the same as the original one. Okay, and then we ended with this AP problem. So what I think I want you to do is I want you to play around with this, but in no way are you guys really totally ready for this. So we did a lot of, they tried it for a couple minutes, but it really turned into me talking about some things, which is okay. Again, it's very, very early on in the process. The other thing I want you to do is get everybody's notes and see if I know there's some other stuff we talked about, so I want you to make sure if I threw a couple other examples on the whiteboard or something that somebody got those down. But definitely let's talk about it when you go over it, and we'll see what you have questions on. All right, I hope this helped a little bit. We'll talk to you soon.